Okay, the Zoom people, you can see the screen on your computer, this one. Anyone is on Zoom? No, no one. Okay, so we were discussing the energy equation, which is more comprehensive than the Bernoulli's equation, because for energy equation, we can consider the loss also. At the same time, the energy equation can be applicable for compressible and incompressible, both types of fluids, right? So after that, we started working on one example where an irrigation pump, which is used to supply water from this point to this point. In between this point, 2 points, the elevation is 8 feet, and the pump is used to overcome, like to deliver water from these 2 points. And we know the head loss. And the question was, they asked you to find what is the horsepower of the pump, like the pump power in horsepower. And once you know the power, how what will be the efficiency of the pump if the input power is given, right? So what we did, we tried to, okay, so we tried to work on that. At first, we identified all the given values, and then we found, identified what are the final outcome we need to calculate. We did that. And then, since we know the pressure, we know the velocity or something, and the main thing is the head loss was given, so we know that we have to use the energy equation. We can't use Bernoulli's equation because Bernoulli's equation can't handle the head loss, right? So what we did, since the first question was you need to calculate the power, the equation for power was gamma q h pump. We know the gamma, which is 62.4. If it was something else, some other fluids, we need to use the gamma of that fluid. We know the q, which was given, and the only thing we didn't know was h pump. So to calculate that one, we started to use the energy equation, right? And we applied the energy equation between 2 points, starting point of the pipe and the end point of pipe, because we know the head loss for the pipe. We don't know anything about data loss on everything. Okay. Is that the enough brief of class example 15? I know over the weekend you don't remember anything, so I hope that helps. Okay, so we applied that, and for each term, we tried to identify what would be the value for that. We discussed, or you already know, if any surface is open to atmosphere or water is discharged into open atmosphere, the pressure will be 0, right? Gauge pressure. Also, we know whenever we have any open reservoir, on top of that, we can consider the velocity is very, very negligible. We can consider that as 0. It's not 0 actually, but we can consider that as 0, right? And there was no turbine, nothing. So PB was 0 also. You calculated the FB, we calculated the ZB. Now, I think we stopped at head loss. If you read the question, you will see the head loss is given per unit length of pipe. So you know the head loss for per unit length of pipe, which is 0.1 foot per foot, right? That means we need to know what is the total length of pipe we are considering. So since we are starting our calculation from A prime to B, that means that is the total length of the pipe, right? And what is that length? 15 feet. So length of the pipe. So that's what we did. 7 plus 8, 15. And we multiplied with 0.1 because that was the per unit length loss. So now we have everything. What we will do now, we will calculate the H pump, and we will see how that value differs from 8 feet, because from this image we can see the pump is actually lifting water like for 8 feet, right? So we need to calculate what is the energy this pump is giving. So that's what we will see here. Yes. VB is from here. The QB was given and the diameter was given. So you can actually calculate the area of the pipe, right? And if you know the area of the pipe, you can actually calculate the velocity inside the pipe here. So this is the VB. And what was the other question?
Where's the 7 times 8 after head loss?
Oh, here. So point 1 is what? Head loss per unit length of the pipe, right? So we need to know the total length of the pipe. So total length of the pipe is what? From this point to this point is 15, right? Okay. So what is head, pump head you got? Say it again. 11.12. All, and what will be the unit? It's head, and we are using the FPS system, so feet. Okay. Now, are you seeing something? The pump from this diagram, it is kind of like, you can see the pump is actually lifting water for 8 feet, right? But the pump head, you got what? 11.12 feet. Why we are having these extra 3 feet of head or energy from the pump? Not gravity, friction, because the pump has to overcome friction and then it has to lift water these 8 feet. That's why obviously whenever there is a head loss or something, the head pump head will be higher than the what is the actual depth it is lifting the water. Okay, so all of you got pump head 11.11 feet. You can do the calculation properly. Once you know the pump head, can you add that pump head here? 11.11 feet, and give me the value for the power. Okay. And this power is actually the power output of the pump, right? From the pump, we are getting that. Gamma QH pump. So gamma is 62.4. I will write down the unit also so that we can cancel. Feet cube. And now we got 11.11 feet. We can cancel feet cube, feet cube. Finally, what was the answer? 13. This one, right? Now this is the answer. This is the answer for the power of this pump, but this is not the answer what we are looking for. In the question, they said that you need to state the power in horsepower. That means we need to convert that into horsepower, right? So in your question, you know the conversion factor, which is 1 horsepower equals to 550 this one. So how can, what will be the horsepower for this power of the pump? Okay, so 550 horsepower, 2.52 horsepower, right? Now that is the answer for the first part. That 2.52 horsepower. Okay. And the next part is you need to calculate the efficiency. That means with considering all the losses and everything, this is what you got. That means, and you know what amount of power was supplied in the system. So can you calculate the efficiency? Okay, how can we do that? Okay, everyone is done with this slide. In the back, you're done? Okay, so the efficiency power output over power input. That means you got 2.52 horsepower, 2.86 horsepower, 0.88, right? Now, if you keep that in that way, that is correct answer. But for any reason, if I ask you to calculate the efficiency in percentage, usually we consider we express the efficiency in percentage. So what you will do, you will just multiply that by 100 and you will get the 88% efficiency. Okay, that means if you supply 100 horsepower, this pump can give you 88 horsepower, and 12% is getting lost due to different type of friction loss and everything. Okay, if there was no loss, nothing, you would get like 100% efficiency. That is not true. That is never happening. So that's it for energy equation. Like we discussed how it is different from Bernoulli's equation. How can you calculate the head loss? How can you find the pump head and power and efficiency and everything? Now, do you have any question about any concept, any calculation procedure, or anything in general from energy equation? I was that good that you don't have any question? Before test, you will know that you have so much questions and I have to spend 2 hours. Okay. Okay, so I was so good and you don't have any question. That's great. So I will start the next thing, which is the conservation of momentum. That is the last thing we will cover before your test 3, which is on 17th. But all of you should have a photocopy of 3 examples. Do you have that, all of you? Make sure you have that 3 examples, 5.10, 11, and 12. That is from your textbook. These 3 questions, that is about the energy equation. It's just few extra problems for your practice about the energy equation. Please go through these problems, and if you have any question, just let me know. And if you think, no, we need to discuss that in class, we'll do that. But please go through these class examples, okay? Okay. And then now we can start our conservation of momentum equation. And it will take 1 minute to open the new file. Okay, the Zoom people, you can see this screen on your computer. Okay, so we completed class example 15. We went to lab to demonstrate the Bernoulli's equation. So first 2 are done. Now the class lecture you have, that is for this whole week, like for next 3 lectures. So please make sure you bring that Wednesday and Friday. What we will do here, we will start discussing the general momentum conservation. Then we will come up with the equation for the linear one and then the angular one. Okay. Once we start the momentum equation, you will see that you kind of know what is already like momentum equation. You already know that from your physics in high school, I guess, right? So tell me what is moment, like whenever you hear the word momentum conservation, what is the first thing come to your mind or something like that? M1 V1 equals to M2 V2, right? It's just like the momentum on one side is equal to the momentum on the other side, right? Okay, and momentum is actually what? Mass times velocity. Okay, so I'm pretty sure you saw this example of like rocket, because this is the fuel, and M1 V1, it's coming out with a velocity, and to balance that, the rocket is moving on the other direction, right? At least we saw that example in our physics book all the time. Okay, so it's like the momentum on, if you have momentum on the other side, you have to move on the other side, opposite side, to balance that momentum. Another example can be if you do hunting, like if you whenever you use that gun, obviously you feel a thirst on the opposite direction, right? That is again the momentum conservation. This is another example. This is called flyboarding or something. So the water from this area, it is coming on this side. To balance that, you can move on the other side and you can feel like super, or maybe Iron Man, I guess. Okay, so all of these are kind of momentum conservation, like total momentum is constant in the absence of any external force. But if there is any external force, it will be the summation of external force. So that is the momentum conservation. But for fluid mechanics, it is a little bit difficult to get what mass of moving fluid we should use. So that's why we use a little bit different expression for the equation, but the concept is same. And we will get that expression from a very known equation, Newton's second law of motion. You know that equation, right? What is the Newton's second law of motion? F equals to mass times acceleration. That is basically the momentum equation. You will see that. Okay, so now the next question is, why should we know about these one? Like there are hundreds of things we know, but for this class, why should we know about that one, right? So the momentum equation is important to know the force for moving fluid. Okay, if we want to design a sluice gate or a flow diversion valve, like flow diversion valve that is used in industrial purpose, you can divert the flow from a silo or like conveyor to different direction. So when you will design that, you need to know what amount of force from the fluid is coming. And that's why we need to use the momentum equation. Do you know the purpose of sluice gate? The purpose of sluice gate or flood control gate or something like that? Okay, you can see the sluice gate or flood control gate, something like that, to any dam or something. What they do, it is kind of, when it's closed, the water on the other side can't pass or can't come to this side. If you want to protect the lower end people from the flood, you can use this gate and it will hold the water for a certain time. And then you can release the water slowly so that there will be no flood on the downstream. Okay, so that's why it's called the flood control gate also. Okay, so to design those, we need to know the force, and that's when we need to know the momentum equation. Okay, so you told me the momentum second law of motion is F equals to ma, and A is acceleration, and how that is related to velocity. The change of velocity over time is actually the acceleration, right? So that means d over dt mv, and mv is what? Mass times velocity is what? What is the name of mv? Momentum, yes. And you see, it says that the change of momentum equals to F is actually the force, right? So change of momentum is equals to the summation of force. And see, you know that already. It's just we stated in different way for momentum conservation. But you already knew this equation, right? F equals to ma. Okay. So that's the momentum equation. But what we will do, we will come up with the expression which we can use for all the other calculations that control surface, control volume, and everything. That's what we will do. So let's work on that Reynolds transport theorem. Do you remember that equation, Reynolds transport theorem? There was something through the control surface, and there is something within the control volume, like this classroom and everything. And finally, what was the total change within a certain time? We discussed that, right? Now, there is one typo here. That should be T, not X. That should be d over dt, CV, eta rho dV, and that should be the volume. Now, if you can remember a little bit, this equation was we had to deal with the extensive property, which is a property which is dependent on mass. For this case, it will be momentum, which is mv, and the intensive property was n over mass, which is independent of mass. So mv over m, that is just v. Okay. Now, instead of n, we will use mv, and instead of eta, we will use v. So that equation will be control volume. For eta, it will be v rho. Whenever you see one line with v, that is actually for the volume, right? You know that. And for control surface, CV is for control volume, CS is control surface. Okay. Now for this control surface, are you seeing there are two V's here? So you may ask, ma'am, can we square the velocity? No, we can't, because each one will express something different. So we will always keep as like them separate, okay? And we will name that separately, but let's work on that. So this is the equation, right? For the linear momentum. Okay. So if you are done, I will go to the next slide. Now, d over dt mv equals to what? From the Newton's second law of motion. D over dt mv equals to what? Summation of forces, right? So we will just replace that. Everyone's done here? Okay. So what we will do, for this one, we will say this is the summation of force. And again, that should be T. Please fix that typo. That was unfortunate, but anyways, fix that. Okay. So that is the final equation. For any type of flow, steady, unsteady, anything, but we already discussed for this class, we will only use the steady one, so we can simplify more. But before that, let's discuss three types of velocity here. What are the meaning of each velocity term here? Okay. So let's move to the next slide here. And I fix that is T. And I will number each velocity. This one is number 1. This one is number 2. And this one is number 3. Can anyone read the very first one? Point number 1.
Velocity of the fluid system at points within the control volume.
Okay, so number 1 is, this is the velocity of the fluid system at any point within the control volume. Okay, what about number 2? Who will read that?
Velocity of fluid passing through the control volume.
Okay, so for number 2, this is the velocity, like at which velocity you came to the class and you jumped out of the windows. That velocity it was, and it can be like perpendicular to the surface. It can be in different angles. That's why it has components. So it can be Vx, Vy, Vz. Okay, so it can have 3 different components. And who will read the very last one? Read that. No one from the last bench. Where is Derek? He's not here. Okay, William, you read that. Mm-hmm. Okay, so the first one was the velocity through the control surface, and the final one was the velocity with respect to control surface. So that's why for this one, we will always say VF, like velocity of fluid with respect to CS. Okay. So you will see how these 3 can be different, and that's why we are not squaring the velocity, because these 2 are a little bit different from each other. Okay. Okay, so the next, you all have this text on your copy, right? Okay, so the next one will be this type. Again, this should be T, and again, this can be Vx, Vy, Vz, and this can be Vfcs. Okay, so that will be the final equation for the momentum conservation.
All those V's, the VX, VY, VZ.
No, just this one. Oh, that's what you are asking? No, this one is V, that is the volume, and all the other V is velocity, some sort of.
Just like a linear velocity, but that's like a triple. That's one that's like in 3D.
Yes, if you have like flow in 3 direction and you need to calculate in each direction, yes. So that will be the velocity which will take care of the components of that. But if we work with just 1 dimension, we'll see one example within few minutes. Okay. Now, you know from your experience, we always simplify with something. So that's what we will do here. This equation is for steady, unsteady, any type of fluids, and we were missing you. Yeah, we needed you for something. Secret. Okay, now, so for steady, we said that for unsteady, we will not discuss anything unsteady here. So this term can be, the very first term can be what? 0, right? Okay. So for steady flow, this whole term is 0. So finally, for steady flow, the equation will be CS V rho okay. this one. And there we can do one more simplification for incompressible flow when the density is not different, density is same. So that will be the next simplification. And we will see. Everyone's done to this slide. Okay. So if we have the incompressible, or if the fluid is ideal, then rho is constant. So it will be just F in the summation of V rho okay. And you will see most of the time we are using this one because most of the time we will deal with something related to water or something incompressible fluid. Okay. Okay. So there is one example just to explain what can be each term. This one, but before doing that, okay, no, let's do this one first. Okay, so for this one, this is a pipe through which the water is flowing. This is the inlet. You can see that. This is the outlet. Okay. Now, for momentum conservation, we need to work with like either or X direction, Y direction, or Z direction. So as an example, here we will work with X direction. Okay. So here, X direction, the positive direction in this way. That's what we will do here. And you can write down this one. Px rho outlet minus Vx rho inlet. Okay. So for inlet or outlet, so for outlet, everything is already in positive direction. You can see that, right? But for inlet, this V in, it's on the different direction. We'll work with that, but that can be the final summation of force in X direction. Okay. Okay. And now we need to know one more thing. When we say the summation of force, so what can be different type of forces we can have? So that is just the next part or next slide here. We can have 4 different types of forces here. The first one you already know, which is number 4 here, but that's the one which is the easiest, the weight of the fluid. In which way it will work? X direction, Y direction, Z direction, horizontal direction, vertical direction. In which direction the weight will work? The vertical direction, right? Or Y direction. Okay. The another one can be the pressure force that act on the open control surface, like here. That is another type of force. If it's not given, we will consider the atmospheric pressure. If it's given, we will use that. There can be 2 other types of forces. The one is resultant normal force from the solid boundaries on a closed control surface here, which is perpendicular to the surface. Another one is resultant shear force from solid boundaries on a closed control surface. So shear force is what? In between layers. Okay. So we will start from this point. Please bring your class lecture. We'll start from this point and we'll do some calculation. Okay. Thank you, class. I will see you on Wednesday.